Good morning. Here we are once again at the physics video lecture. Psci 168, video lecture 24. So we're deep in the heart of thermal physics. And we'll start with the review of the most important concept we got to last time, right? We had done the butter candle and the calorie. But then we found the mechanical equivalent of heat. And I'll say a couple more words about that, or just really reiterate. This is so important. So the mechanical equivalent of heat, it's just an equation, it's just a number, but it means a lot. So 1 calorie equals 4,186 joules. And we know that we generate that heat, I gave an arrow from this direction over to there. We generate that heat using friction. Okay, so here's the thing. This side of the equation, right, this is just an equation, good, a definition, so to speak. But this side here refers to everything we learned when we were talking about thermal physics. So this is the thermal physics side. And this here is the mechanics side. Remember, we call our subject mechanics, and forces, work, energy, etc. So over here is mechanics. And so, say I give you an exam question I want you to write about, or say what is the mechanical equivalent of heat and how is it determined, and that type of thing. Then you would just start with this definition, but there's all kinds of content here, right? Over here, you're just talking about the whole thermal physics world. Over here, you're talking about the whole mechanics world, and or a good part of it. And I'll even put that little arrow here. We got that via friction. Okay. But the thing is, here we're talking about energy. We have energy conservation. Okay, so long story short, this is a really rich topic. And so when you have this definition here, you wanted to evoke all of these topics that we worked on. Now, so that was the first thing. Then we also had once we had this, we could discuss the specific heat capacity. Specific heat, and let's just go ahead and write this. Well, where's our cartoon? Q refers to thermal energy, and we're just applying it to something, and then we say that it causes the temperature to change. Okay. So this formula is also very important. And after determining this, then we were able to express thermal energy as energy in terms of joules. Okay. So in a sense, we've left the calorie behind, but it's always there in the back of our mind. Good, so specific heat. And now I'll get to what I had put on the board at the end of the last hour. And and I had you guys look up some of these specific heats here. Yeah, just for the record, in fact, I'm going to use that, so let's go ahead and put that up here. The specific heat of water, 4,186 joules per kilogram per degree Celsius. And the specific heat, so that's liquid water actually, specific heat of ice equals 2,090 joules per kilogram degree Celsius. And you guys were going to look up a whole bunch, or a half dozen more of these, just to get an idea. Turns out water is really at the very top of the list for a lot of specific heat capacity, which means that this mass, say if it's water, can soak up a lot of heat, Q, without changing temperature that much. Okay, good. So yeah, we're going to use these, and now let's go to phase transitions. So this is our topic that we left off with last time. I was talking about ice melting to a liquid and then vaporizing. And that's referred to as phase transitions. Talking about the states of matter, we also refer to them as phases. States of matter, solid, here, let's write that better. Solid to liquid, and liquid to gas. Solid to liquid, so that's a phase transition, and liquid to gas is also a phase transition. What we're going to look at is just the example of water. So, we're going to add some energy to water. So let's start a big graph here, and we'll label it and discuss it. So this here is going to be the temperature in degrees Celsius. We'll leave some room for negative degrees too. And this is going to be energy, thermal energy in joules. And what we're doing is we're adding thermal energy to 1 kilogram of water. Adding heat, we'll just call it that, to 1 kilogram of water. So that's what this graph is about. And so here we go. Let's start with water that's at, say, just to start with some concrete number, minus 20 degrees Celsius. So that's ice. And then 20, 40, 60, 80, 100. So right here is 100 degrees. Right there. And we have ice at minus 20 degrees Celsius. So we want to heat it up. It's not going to, we're going to heat it very slowly, so it's actually not going to melt immediately. It has to make it to 0 degrees Celsius. So there is a straight line there, and in keeping with this formula, okay, this is Q, right? So we're adding heat to that 1 kilogram of ice and raising its temperature. And here we would say we have Q is equal to mc sub ice T minus T sub 0. That's what my delta T is. That's the change in temperature. And if I went from minus 20 to 0, then that would be 0 minus negative 20. That would just be 20. Okay. So in our example here, that's just 20 degrees. Equals 20 degrees Celsius. In our example. Okay, so here's where it gets interesting. So and you can imagine if you were to do this practically, you could have it in a freezer that's set at minus 20, and then you turn the dial on it to say minus 5, and it gradually gets warmer without melting, okay, because it's still minus 5. Turn it to minus 1, gradually warms up to minus 1. So now it finally gets to 0, and here's what's interesting. As it melts, it does not change temperature at all. So it melts very slowly. So this is the melting curve, and it's just level. It's a melting section there. But it takes energy for it to melt, okay? And quite a bit. So let me go ahead and write this. Q is equal to M times L sub F. So that's a new quantity. Okay. It's not this formula here because the temperature is not changing, but a lot of energy goes in to melting it. This L sub F I'll write over here. L sub F is called the latent heat of fusion. Okay, latent heat of fusion, and that means it's proportional to the mass, but M times L sub F is some number of joules. Okay, so latent heat of fusion, LF for water equals 3.33 times 10 to the 5 joules per kilogram. Okay. So if we're doing 1 kilogram of water here, 3.33 times 10 to the 5 joules. Now we don't usually memorize numbers, but we have to make some sense of that, because that is a tremendous amount of energy actually. Hold on to that thought. So now it's melted. We're all the way over here. There's a certain Q. And now when it's all 0 degree water, we can turn up the heat and raise the temperature of it. And we're going to have, it's going to be a steeper slope. This is the energy it takes. And now we're actually doing this formula right here with water. So here we have Q equals MC of water, T minus T sub 0. So this T sub 0 really is 0 degrees Celsius. And this T here, when we get up to 100 degrees, that would be 100 degrees. Okay. So in this particular example, 100 degrees Celsius. We could give each of these a name. This would be Q of heating the ice. This would be Q of melting the ice. This would be Q of heating the water. But let's go ahead and compare this. And so here, Q is equal to 1 kilogram times, let's just write it out, 4,186 times 100, and that's going to be joules. We'll plug that in. So what is that? That's 4.186 times 10 to the 5 joules. So this number is important. You take water at 0 degrees Celsius, bring it all the way up to a boil. Takes 4.186 times 10 to the 5 joules. Let's make that more clear to read. 10 to the 5. And you'll notice this number here is about 3/4 of that number. So just to melt the ice is 3/4 of the energy it takes to bring water to a boil. And that's quite a bit of energy. So these latent heats are really substantial and important quantities here. Something we typically have never even heard of. Okay, so what happens when the water has now reached 100 degrees? We keep adding energy, it vaporizes. If you keep it at atmospheric pressure, it vaporizes at a constant temperature. So this is vaporization. And that energy is the mass times the latent heat of vaporization. So L sub V is equal to, called the latent heat of vaporization, and it is 2.26 times 10 to the 6 joules per kilogram. So it takes an enormous amount of energy, almost 10 times as much, 8 times as much or so, 7 something, that much more than this amount here to vaporize the water. So yeah, there's a lot of energy involved. We're typically just, this is the curve we're familiar with. Throw water on the stove, heat it up. This is the curve we're familiar with, but we're not actually familiar with these amounts of energy here that are substantial. Okay, these types of quantities, latent heat, of fusion and latent heat of vaporization, I've just given you them for water. Okay, so this is also water. I should write that. Water. Different substances have different latent heats. We're not going to go there. You can look them up, make a big table of those as well. But yeah, we definitely want to be aware of this. And the best way to do it is to know these formulas and look at this graph. So if we return to this graph, we heated the ice till it was 0 degrees, and then we added energy, and it melted, but the temperature didn't change. So when it was completely melted, 0 degrees Celsius, then as adding heat, we could bring it up to a boil, to 100 degrees Celsius. And then if we keep adding heat, it vaporizes till it's all a gas. And the energy amounts are so substantial that you really have to know this. Good. So the next thing we're going to do with this is talk about getting the energy back again. So if you put all of this energy into the ice, you melt it, put more energy in, heat it, put more energy in, vaporize it, can that energy be returned? And the answer is yes. Remember, the energy is neither created nor destroyed, so we just have to track it down. If you were to look this up, you'd see this graph. It's all over the place. It's just a standard and very good way to look at these things. Good. Now, the reverse process. This I'm going to do with that cartoon I had on the board the other day. This is as good a way as any. So we've got the block of ice, and then we add heat, and it melts. So now we've got a beaker of water, and if we keep adding heat, I'll call it's a gas, so it's in a balloon just to keep it in place. Okay. So what do we have there? This is adding energy. So energy is added, or we could say, let's say energy is absorbed. That might be better. Energy is absorbed, so this is ice, liquid, water, and this is gas. Okay, so solid, liquid, gas. How about we do this? This is water, solid, liquid, gas, and the system is absorbing energy. So this was melting. Got another color here, why not? So this here is the melting process, and this is vaporizing or vaporization. And this is what we're familiar with, right? We add energy to something, melt, vaporize. But the other direction of the arrows is also possible. Make sure these arrows are pointing, okay? So this direction as well. So we can go from a gas to a liquid, and then we say the gas is condensing into a liquid, condensation. And then if we go from a liquid to a solid, of course, it's freezing. Okay. Here's the thing, we now know that there are enormous amounts of energy involved here, okay? Well, that means, and by the way, when it's liquid and we're heating it up, there's of course that enormous amount of energy as well. This one. Well, that energy is not lost. So if gas condenses to a liquid, this much energy is being released per kilogram. And if gas or if a liquid freezes to a solid, this amount of energy is also released, right? The corresponding amount of energy. Energy is absorbed here, here energy is released. And I have a good homework example for you guys. So homework. We want to get some images. Like I said, this energy being released is not commonly something we're aware of, but it's used, right? It's a phenomenon that you, for example, if steam gets on your skin and condenses, you feel a pretty aggressive little steam burn. That's the condensation, that's energy being released. But what we want to talk about is the energy that's released when a liquid freezes to a solid. And we have that in the local citrus orchards. So citrus orchards are often, when a really cold freeze is forecast, the orchards will actually be watered. You'd say, why would they water the orchards at that time? The reason is that water will, in freezing, it will release so much energy, it will avert a deep freeze, a really harmful freeze. And let me draw a little cartoon to illustrate how that works. Okay. So the idea is this: you've got a citrus tree, okay, with all its oranges on it. Oranges, reds in our book, okay. And let's go ahead and we can either spray the orchard or we can even put some water here on the ground. And then a cold air comes in from the mountains, okay. Very cold air. Now suppose this cold air, I'll just make up a number, is minus 5 degrees Celsius. Right when it's starting to get dangerous, okay. So say it's minus 5 degrees Celsius, and the water has been actually getting colder and colder and giving off energy, and now it's about to freeze, so the water is at 0 degrees Celsius. Well, which way does energy flow? The energy goes from the higher to the lower temperature, and the 0 degrees is the higher temperature. So the energy will be released from the water, and there's quite a bit of it, and it will warm up the air. The idea is maybe it warms it up to -1. Okay. -1 is better than -5, right? So this is what's done in the citrus orchards. Freezing water releases heat. Releases heat. Now, it's not the kind of heat that you can stand in front of it and, like a fire, and rub your hands together. Nonetheless, it is releasing heat. And let me bring our old cartoon into play again. This is always the case. The spontaneous energy flow. Right, this is our cartoon for energy flowing from higher to lower temperatures. Now that I think about it, I'm not sure if I've introduced that one yet. Well, we're going to see it a lot in future. So, even though this is water at 0 degrees Celsius, air at -5 is colder, and the energy flows, here we'll even put a Q in here, energy flows from water, let's say water at 0 degrees Celsius flows to the air at -5. And hopefully warms it up, warms it to -1. Good. No damage to the crop. Yeah, this is that cartoon that we're going to use a lot in terms of the direction of heat flow. Okay, I mentioned a homework. What I'd like you to do is see if you can find some images of citrus orchards in which water is, being frozen with the purpose of saving the crop. Okay. So homework, find images. That'll make your notebook more colorful. Citrus orchards. I've seen it here around town before. In fact, where I was driving north once, clear day, winter day, everything very, very cold, just ice all over the citrus trees. So that's what was being done. I'm going to consult the clock here, see what's going on. Okay, excellent. So that's actually a pretty major chunk of physics that we're talking about, but we need it. And like I said, this is a really nice concrete example. Space this stuff out a bit because there's a lot of content here. I'm going to return to our asteroid in a moment. So we now know quite a bit more about energy because we brought thermal energy into the mix and we're relating it to mechanical energy. So that's what I want to return to. Before I do the asteroid, I'm just going to talk about a bullet being fired against, say, some steel plate. So energy, let's call this mechanical energy and thermal energy. We already know that with friction and force, right, we can turn mechanical energy work into thermal energy. So let's return to our asteroid. We'll start first of all with a bullet fired against a steel plate. So we have, okay, here's a picture of our bullet zipping along. Here's the steel plate that it's going to hit. Okay, and the point is here, it's not going to damage the steel plate at all. Okay, what is it going to do? It's going to heat up and melt and potentially even vaporize. Okay? Some combination of that. It's going to, or fragment and splatter, vaporization. Maybe that's a little bit ambitious, but it can heat up and melt and fragment for sure. Okay? So there's a bullet. We have 1/2 mv squared, just like with our asteroid. Remember the asteroid, we said it's going to dig a big hole in the ground. The bullet's not going to do that. So when it hits the steel plate, it's going to turn into basically heat plus kinetic energy of the fragments. Okay. Kinetic energy of whatever fragments, whatever happens there. Okay. But it will definitely quickly heat up to melting temperature, or it definitely can. Depends on the metal of the bullet. And in terms of the amount of heat, well, if the whole mass of the bullet gets heated enough to melt, then you could have something like M specific heat of whatever metal that is times T melting minus whatever ambient temperature you have. Okay, so that would be a proportion of that energy. And if there's leftover energy, it could be, fragments could be splattering out. Okay. Now, not knowing anything about the fragments, you could turn this around and say, okay, that's the same mass, right? So if you know the melting temperature of whatever particular metal it is, you could figure out how fast does it have to be going to completely melt. Okay? So that would be an energy conservation thing. So we can ignore the kinetic energy of the fragments and say, how fast does it have to be moving in order to completely melt? I would call that a homework, but I'm just going to solve it. Okay. How fast for complete melting? Actually, this is a good homework problem. Let me set it up. So what we're looking at, your answer. I'll set it up. So what we're looking at is 1/2 mv squared equals mc T melt minus T0. Generally, we just let that be 20 degrees Celsius. That's just the standard. Room temp, basically room temperature. Okay. Well, notice, mass cancels, and okay, just to be concrete, let's let that be lead. Okay. Specific heat of lead, as an example. And then we're going to solve for V. Solving for V. V would be equal to 2 specific heat of lead. Then you'd have to look up the melting temperature of lead minus 20 degrees Celsius. And the 2 there, you'd have to take square root. This would actually tell you how fast the bullet has to be going to completely melt when it hits that steel plate. Okay. So if you can, actually you can do this pretty easily. Just look up the specific heat of lead. It's very small. It's like 100 or 200 or something, a couple hundred. Melting temperature of lead, it's only a few hundred degrees Celsius. You know what, I'm going to call this homework. Like I said, you need the specific heat of lead equals and T melt of lead. You have to find the correct units, but you can probably look this up in 1 minute, right? See what happens. Good, so that's mechanical energy and thermal energy. If you just take pure kinetic energy and motion, turn it into heat. Bullet's a good example. The other example, let's return to our asteroid. See, knowing that this kinetic energy can essentially be completely turned to heat, we do have to revisit the asteroid, because there we required it to be completely turned to work. Well, we did talk about the heat as well. So my second example is the asteroid again. And in fact, I'm just going to write down and what we had before and mention it again, just to bring it back into consciousness. So for our asteroid, and in fact, how about the Arizona meteor crater? There we had, the thing coming down and it's going to blast a crater out of the ground, right? So there we had 1/2. There's the thing's going to come in, blast a big crater out of the ground. So what do we have? We have 1/2 mass times speed squared for our asteroid that's coming in there. And then we're just going to say it was equal to work of excavation plus heat of the explosion. Okay. Again, plus a bunch of fragments and what have you. So what we did last time was we really just focused on this, but now we know there's, and if you read up on it too, you know it's a gigantic fireball and a tremendous amount of heat produced as well. So we definitely had 1/2 mv squared is equal to the work plus the heat. We can't say much more about that, about the ratio of it or anything like that. Work plus heat. Okay. The fact that it dug a big crater tells us, yeah, that work was done. The amount of heat that was produced, that's a more complicated problem. Okay, so that is the subject, mechanical energy and thermal energy, and returning to those collisions. I think that'll be good for today. Yes, that's actually quite a bit. So again, see what number you get on this speed here. I can look it up later too and put it up on the board next hour if anybody's interested. Shouldn't be hard to find these numbers. Specific heat of lead, melting temperature of lead. You gotta get the right units for both of these. Multiply them, take the square root, and see what happens. Okay, see you guys next time.